You know, when we talk about digital security, we almost always use the word strong, a strong password, a strong firewall. But what if that's not quite the right word? What if the goal isn't just to be strong, but to be resilient? So let's dive into what that really means.
See, it's tempting to think of your cybersecurity like a single massive castle wall. But that's not really how it works anymore. It's much more like a team. You've got all these different players out on the field, your antivirus, your firewalls, your intrusion detection systems, and they're all supposed to be working together to protect you.
And that's the real kicker, isn't it? How do we know the team is actually playing like a team? I mean, if every player is just doing their own thing, are you really protected? Or are there these huge invisible gaps in your defense that a clever attacker could just waltz right through? This is the exact problem we're going to unpack today, and it's based on some really cool research.
And that big question leads us straight to what you could call cybersecurity's teamwork problem. Honestly, it's a massive headache that security engineers deal with every single day.
It sounds so simple, right? If you want better security, just add more tools. Throw in another network intrusion detection system, a NIDS, and you should be safer. But it turns out it's not that easy. In fact, sometimes adding more players just adds more noise, more chaos, and can actually make the entire system less effective.
So a big reason for this mess is something called the base rate fallacy. Okay, imagine you have to find one single needle, one malicious packet in a haystack the size of a mountain. That's what these security systems face every second of every day. There's such a massive flood of normal traffic that even a super accurate detector can just get buried in false alarms, making it pretty much impossible to find the real threat.
And all this points to a huge shift in thinking that we need to make. For a long time, we've been focused on the stats of the individual player. You know, how fast is this tool? How accurate is that one? But what we really need to be measuring is the reliability of the entire system, the whole team. And maybe most importantly, how resilient that team is when a smart attacker is actively trying to fool it.
So how in the world do you measure the performance of the whole team? Well, some researchers have come up with a totally new way to look at this problem. They call it an Information-Theoretic Framework.
Okay, I know that sounds super academic, so let's translate that. What they're basically saying is that a good security system isn't just one that screams danger all the time. A great system is one where, when an alarm finally goes off, our uncertainty just plummets. We go from, is this something? To, oh yeah, this is definitely something we need to look at.
And they've managed to boil this whole concept down into one powerful number. It's called the Intrusion Detection Capability, or CID for short. Just think of it like a final grade, a single score from 0 to 1 that tells you how much useful, actionable information your entire security team is actually giving you.
So how does this work? Well, the framework models the whole detection process as a chain of events in 4 simple steps. It all starts with X, the true state. Is this thing an attack or is it normal? Then that data gets turned into Z, the digital footprint, which is how the computer system actually sees it. Next up is C, the classifier judgments. This is where each of your security tools gives its opinion. And finally, you get Y, the final alarm, the system's one final decision.
Now here is the genius of this whole thing. At every single step in that chain, from X to Y, information can get lost. The data could be represented poorly, a tool could make a bad judgment call, the final decision could ignore the right tool, and this framework lets us measure exactly how much information is being lost at each stage. It's like finding the exact weak link in the chain.
All right, enough with the theory. Let's see how this actually works with a real-world example from the research paper. This is where it all starts to click.
Okay, check out this table. It's breaking down the system's performance. We start with the raw data, the feature representation, which has a nearly perfect CID score of 0.999. All the info is there, but watch this. We add our first detector, a machine learning model, and our score drops to 0.629. Ouch. We add a second, different detector, and hey, the score goes up to 0.809. We're getting better. But then, after we add a simple block list and combine everything, our final system score actually drops down to 0.701. We literally made the system worse by adding more tools. This shows you clear as day that just piling things on is not the answer.
And I want to be clear, this isn't just some random idea. This is a serious framework that was published in the peer-reviewed journal Computers and Security. It's designed to give security engineers something they've never really had, a kind of homepage for their entire system's health, a single dashboard to see the big picture instead of just a bunch of disconnected stats.
So the system works okay on a normal day. But what happens on a really bad day? What happens when we put this whole thing under some serious pressure? Let's find out.
This is it, the ultimate test. The researchers simulated an attack from what they call an adaptive adversary. We're talking about a smart attacker who has done their homework, they know how your detectors work, and they are specifically crafting attacks designed to look like normal traffic. This is where you find out if your system is just strong or if it's truly resilient.
So here's our baseline, our before picture. On a totally normal day, our two main detectors, the LSTM and the MLP, are doing a pretty decent job. They've both got scores above 0.6. Everything seems fine.
And now, look at this. Under attack, the first detector, the LSTM, just completely falls apart. Its score collapses from over 0.6 all the way down to a measly 0.023. It's basically useless now. But look at the other one, the MLP. Yeah, its score dropped too, but it's still in the fight. It hasn't been totally tricked. This chart just makes it painfully obvious. That first detector, the LSTM, got absolutely crippled. So the big question is, why? Why did one get taken out while the other one held up so much better? It's because they were looking at the data in fundamentally different ways. The attacker's trick worked on one, but not nearly as well on the other.
And that, right there, is the entire secret to resilience. It's redundancy. But not just having two of the same thing. It's about having different kinds of players on your team. Players with different skills, and more importantly, different weaknesses. So when one of them gets fooled and taken out of the game, another one is still on the field, ready to pick up the slack.
So after seeing all of this in action, what's the one big lesson we should be walking away with?
Well, here it is. Building truly robust security is not just about buying more and more tools and hoping for the best. It's about making those tools work together intelligently, like a real team. It's about understanding their blind spots. And a framework like this gives engineers the vision they need to find those hidden weaknesses and build smarter, not just bigger, defenses.
Which brings us all the way back to that very first question. As attackers get smarter and more creative, just being strong isn't going to cut it anymore. We have to ask ourselves, are our defenses built to just take a punch, or are they built to adapt, to compensate, and to keep fighting? Because in the world we live in now, that's the difference that really matters.